Quantum mechanics is one of the most important and fascinating scientific theories of our time. It has revolutionized our understanding of the universe at the atomic and subatomic level, and it is at the forefront of modern physics research. In this video, we will explore the fundamental concepts of quantum mechanics and discover how it is being used to unravel the secrets of particle physics. Quantum mechanics, often hailed as the pinnacle of contemporary physics, represents a theory that has fundamentally reshaped our comprehension of the foundational constituents of the cosmos. It exists within a domain wherein particles can simultaneously occupy myriad states, where the mere act of observation precipitates a transformation in the very essence of reality itself. This is a realm where the conventional tenets of classical physics falter. In this extensive exploration, we shall embark upon an odyssey through the enigmatic expanse of quantum mechanics, from its inception to its most profound ramifications. In the nascent years of the 20th century, physicists confronted perplexing phenomena that eluded explication within the purview of classical physics. From the enigmatic deportment of light to the emission of radiation from atoms, the stage was set for a scientific upheaval. The concept of wave-particle duality emerged as one of the most astonishing revelations in the embryonic days of quantum mechanics. It posed a challenge to the very essence of our preconceived notions concerning particles and waves. Visualize the act of illuminating a metallic surface and observing the emission of electrons. Conventional physics would proffer the notion that the energy from the incident light is transfused to the electrons in a continuous manner, akin to the flow of water from a faucet. Nonetheless, experiments conducted in the early 20th century, most notably the photoelectric effect, cast this perspective in a contrasting light. Physicists ascertained that light, conventionally conceptualized as a wave, conducted itself as if it consisted of discrete particles, or quanta of energy. Subsequently, these particles were christened photons by Albert Einstein. The energy associated with each photon bore a direct correlation to the frequency of the light, as opposed to its intensity. Consequently, elevating the light's intensity did not precipitate the ejection of additional electrons, rather, it augmented their kinetic energy. This duality of wave and particle was not confined to light alone. Electrons, traditionally deemed particles, manifested wave-like characteristics, such as diffraction and interference, when subjected to a double-slit experiment. The revelation that particles, such as electrons, could assume the guise of waves fundamentally transfigured our comprehension of the microscopic realm. The mathematical scaffolding requisite for delineating this duality was meticulously crafted by Erwin Schrödinger through his renowned wave equation, which stands as a cornerstone of quantum mechanics. This equation bestowed upon physicists the capacity to compute the probabilities associated with encountering particles in diverse states, signifying a momentous divergence from classical mechanics. The reconciliation of light and particles heralded a paradigmatic shift, laying the foundation for a more profound expedition into the quantum domain. Within the realm of quantum mechanics, particles are characterized by a peculiar attribute that sets them apart from their classical counterparts: the capacity to exist concurrently in myriad states. This phenomenon is designated as superposition, and it constitutes a foundational tenet in the quantum realm. Envision, if you will, a quantum particle, such as an electron. In the realm of classical physics, one would anticipate that it possesses a precisely defined position and momentum at any given instant. However, within the quantum realm, matters are far from straightforward. A quantum particle can exist in a state of superposition, wherein multiple states are endowed with their distinct probability amplitudes. This implies that until the particle is subjected to measurement, it fails to lay claim to a definitive position or momentum. Instead, it traverses a spectrum of possibilities. To fathom this concept, let us consider the renowned thought experiment involving Schrödinger's cat. Within this scenario, a feline specimen is ensconced within a sealed container, alongside a radioactive atom that may, or may not, undergo decay, culminating in the release of lethal poison gas, thereby sealing the cat's fate. Within the precincts of classical conventions, the cat's status is perceived as either alive or deceased. However, within the quantum expanse, prior to the unveiling of the container and the consequent observation of the cat, it exists in a state of superposition, simultaneously embodying both vitality and fatality. Only upon the act of observation does the superposition dissipate, concretizing the cat's status into one of the two aforementioned states. This concept of superposition extends its dominion beyond felines, it extends to encompass all quantum particles. Electrons, by way of example, can inhabit superpositions of varying energy levels encircling an atomic nucleus. This characteristic carries profound implications for the realm of quantum computing, wherein quantum bits or qubits are endowed with the ability to represent multiple states simultaneously, thereby heralding a potential revolution in computation. The comprehension of superposition assumes paramount importance in apprehending the enigmatic facets of quantum mechanics. It challenges the bedrock of our classical intuition, coercing us to embrace a degree of ambiguity within the quantum milieu that stands in stark contrast to our quotidian experiences. At the heart of quantum mechanics resides the Schrödinger equation, a mathematical opus that governs the comportment of quantum systems. Conceived by Erwin Schrödinger in the Annus Mirabilis of 1925, this equation effectuated a tectonic shift in the landscape of physics. The Schrödinger equation serves as the quantum analog to Newton's laws of motion. While the latter expound upon the movement of objects within the classical domain, the Schrödinger equation delineates the evolution of quantum entities, such as electrons and atoms, across the temporal expanse. It provides the scaffolding for calculating the probability amplitudes associated with locating a particle within a specific state at any given juncture. Remarkably versatile, this equation empowers us to scrutinize an extensive array of quantum systems, from the simplest hydrogen atoms to the intricate molecules. It affords us the capability to prognosticate the energy levels characterizing electrons within atoms, the comportment of particles ensnared within quantum wells, and even the intricate ballet of molecules during chemical reactions. The Schrödinger equation unveils an enthralling concept, namely, quantization. In the realm of classical physics, energy flows continuously, unimpeded by restrictions. However, the Schrödinger equation postulates that energy within the quantum precinct is quantized, signifying that it assumes only specific, discrete values. This quantization begets the constancy of atomic and molecular structures, and it serves as the underpinning of the periodic table of elements. Yet, the Schrödinger equation is not merely a mathematical instrument, it constitutes a philosophical portal into the enigmas enshrouding quantum mechanics. It begets inquiries regarding the nature of reality, the role of observers, and the notion of wave functions. It compels us to plumb the depths of our comprehension of the fundamental essence of the universe. We shall unravel the mathematical intricacies enveloping the Schrödinger equation and probe its implications for decoding the comportment of particles in the quantum sphere. Additionally, we shall embark upon a voyage into the mathematical elegance encapsulated within wave functions and the concept of quantum states, thereby preparing the terrain for nuanced discourses concerning quantum measurement and the specter of uncertainty in. One of the most profound and intellectually riveting facets of quantum mechanics resides in the concept of measurement, shrouded in inherent uncertainty. This uncertainty finds its encapsulation in the illustrious Heisenberg uncertainty principle, a tenet that posits the impossibility of concurrently ascertaining the precise position and momentum of a particle with unassailable certitude. Werner Heisenberg's epochal principle emerged from the recognition that within the quantum domain, the act of measurement is not an inert act of observation but a dynamic interaction that disrupts the system under scrutiny. Contemplate, for instance, the endeavor to ascertain the precise position of an electron with a surfeit of precision. In pursuit of this objective, one must subject the electron to radiant illumination, an action that inevitably engenders an alteration in its momentum. Ergo, the more diligently one strives to pin down the electron's position, the murkier the understanding of its momentum becomes, and vice versa. This inherent limitation does not stem from the constraints of our measurement apparatus, rather, it stands as an innate attribute of the quantum milieu. The Heisenberg uncertainty principle radiates ramifications of considerable scope. It challenges the precepts of our classical intuition, wherein we anticipate a definitive grasp over both position and momentum. Instead, it compels us to embrace a realm wherein inherent unpredictability reigns supreme. Moreover, the principle of uncertainty does not remain confined solely to the realm of position and momentum, it extends its dominion to other pairs of complementary attributes, including energy and time. This implies that even if we possess a precise grasp of a quantum system's energy, we remain incapable of forecasting the precise moment of a particular quantum event. Quantum measurement transcends the mere facade of uncertainty, it also elicits beguiling inquiries concerning the role of the observer. In classical physics, observation is construed as a passive act, yet, within the quantum arena, it assumes an active mantle, influencing the eventual outcome. The act of measurement precipitates the collapse of the quantum superposition, compelling the particle into one of its potential states. It shall skim the surface of the captivating phenomenon of quantum entanglement, wherein particles become intricately correlated to the extent that the measurement of one instantaneously bequeaths influence upon the other, irrespective of the spatial chasm that separates them. As we traverse the panorama of quantum science, we shall persist in unfurling the veils shrouding this enigmatic domain, striving to penetrate the profound enigmas and implications of quantum mechanics. The quantum mechanical model of the atom, often designated as the electron cloud model, emerges as a seminal juncture in the annals of scientific inquiry. This model heralded a seismic shift in our comprehension of atomic structure, serving as the bedrock upon which modern chemistry finds its footing. Before the advent of quantum mechanics, the prevailing paradigm depicting the atom was the Bohr model, postulated by Niels Bohr in 1913. This model portrayed electrons as orbiting the nucleus along well-defined trajectories, akin to the celestial dance of planets around the Sun. However, the Bohr model encountered its limitations, failing to elucidate the spectral signatures of more intricate atoms. The quantum mechanical model, which materialized during the 1920s, proffered a more precise rendition of electron behavior within atoms. Instead of positing fixed orbits, it introduced the concept of electron orbitals, regions in the spatial continuum